Hello everyone. Welcome to the presentation on our paper titled Channel Emulation for the Characterization of Wearable RFID Systems. My name is MD Abu Saleh Tajin. I am a PhD student from the Department of Electrical and Computer Engineering at Drexel University. The other co-authors on this paper are Marko Jakovic, Dr. William Mongan, and Dr. Kapil R. Dandekar. I will start the presentation with the motivating factors behind this paper and briefly introduce the system, hardware, and the experimental setup. We will end the slides with our findings and future work. In real experiments, RFID transceivers and antennas communicate through a wireless channel. However, in channel emulation, the physical environment between the RFID transceivers is replaced by a virtual channel. The virtual channel is pre-simulated, stored, and run in a hardware machine. Ultra-high frequency RFID channel emulation is important for the characterization and comparison between different tags and systems. We can have a large supply of controllable and repeatable sensor data that can be provided to real hardware. In contrast, having a large supply of controllable and repeatable data through real experiments is very difficult, time-consuming, and costly. Using channel emulation, we can generate data that can be used to train machine learning algorithms. We can replicate real-world scenarios using channel emulation. This is more relevant in the current pandemic situation we are living in. For example, we can emulate the behavior of a wearable sensor on a patient who is in a hospital environment. Although channel emulation has been used in wireless systems research before, we are the first to report its use for emulating on-body ultra-high frequency RFID sensors. Wearable RFID sensors are generally made with passive RFID chips that do not have any local power source or batteries. As a result, it depends on the interrogation signal from the interrogator or reader antenna. In the United States, the UHF RFID band is 902 to 928 MHz. The RFID tag uses a portion of the received power to drive its circuitry and reflects the rest towards the reader antenna. The reader antenna captures that power, records it, and this is called an RSSI or Receipt Signal Strength Indicator. In our paper, we show channel emulation with a wearable respiration sensor that is called the belly band. The belly band is a flexible knitted antenna that is fabricated using silver-coated nylon. Here we can see three different generations of the antenna. The belly band is periodically stretched and relaxed as the user breathes. As a result, the tuning between the chip and the antenna is disturbed, which gives rise to fluctuating RSSI as we can see here. Here we can see the interrogation of an on-body belly band. A commercial RFID reader drives the interrogation using a directional and circularly polarized reader antenna. The RSSI is stored in a computer that is connected to the reader via Ethernet. We fabricated 1.6 mm thick FR4 boards for accommodating the RFID chip during the emulation. Now, RFID chips have balanced inputs, whereas coaxial cables or SMA connectors, they are unbalanced. As a result, we use a balanced to unbalanced converter between the coaxial cable and the RFID chip. The hardware responsible for the playback of the channel scenarios is called the DYSE. DYSE stands for Dynamic Spectrum Environment Emulator. DYSE can emulate 24 channels simultaneously. In other words, we can emulate 24 ultra-high frequency RFID sensors at the same time using DYSE. This is the block diagram of the channel emulation setup. We use RF circulators to separate the forward and the reverse path. Now we only show the emulation of the reverse channel because the RFID chip we used, it has a wake-up power of around -16 dBm, and the DYSE can safely withstand around -15 dBm power. Compared to the forward channel, the reverse channel power is low. As a result, it's safe for the DYSE. To justify the use of the reverse channel, we apply variable attenuation in 3 channel modes: forward, reverse, and the common mode. In the common mode, both channels undergo identical attenuation. As we can see, the curves follow similar trend for the common and the reverse modes. In real experiments, both channels can be considered identical due to the reciprocity of radio waves. We can calibrate the power level using the RSSI difference between the common and reverse modes. The channel emulation process starts with the simulation of the sensor using HFSS. The scenarios and channels are simulated using a ray tracing software, for example, the Wireless Insight. Then the scenario files are uploaded to DYSE. We run the RFID interrogation and the DYSE channel emulation simultaneously. Besides emulating a normal breathing of 14 breaths per minute, we introduce a 10 seconds gap in the breathing. We used 3 dB difference between an inhale and the exhale state RSSI. This plot shows the RSSI fluctuation due to a normal breathing of 14 cycles per minute. On the other hand, this figure shows that RSSI plot is capable of capturing the no breathing state of 10 seconds. This incident is an abnormal breathing scenario. A decision-making algorithm or a machine learning algorithm will be able to detect this anomaly in breathing, and an emergency notification can be sent to the caregivers. In summary, we developed a UHF RFID channel emulation setup using DYSE. The testbed is capable of emulating scenarios for RFID tags and sensors. The testbed can be used for characterizing and comparing RFID tags and systems. The channel emulation system is an easier, faster, and reliable alternative to real experiments. In future, machine learning algorithms will be used on the data generated by channel emulation. In addition, in the future we will show multi-channel emulation with multiple sensors. For example, we will show the emulation of multiple sensors attached to a person in a hospital facility. Our work is supported by the National Science Foundation, the Department of Education Graduate Assistance in Areas of National Need Program, and the National Institutes of Health. This is the list of references used in this presentation. Thank you very much for your patience.